In this video we're going to look at a problem on fluid motion. So the problem I have is a bucket half full of water, so we can draw a bucket out like that. Okay, and we can, I'll try to get it reasonable looking. Okay, so we can half fill it up with water, and we know that the surface there will just be sitting, it'll just be a flat surface, and that's our water there. And let's say we have a coordinate axis, we'll call that our z-axis, and we can call from that point to there the radius r. Now the idea is that whenever we rotate this water round about, okay, when this bucket's rotated the water will rotate, and when it rotates, if we were to look in at that point there, okay, that's us just looking at it at that level, then if we were to redraw that out, we would be looking at just a flat surface. But when it rotates, this surface will change, okay, the surface will become curved. Okay, now you can go and try that experiment yourself, and a bucket with water and you swish it around about and it'll start in a circle, the surface there will change, okay. So the question is, what's the function there that defines that new surface? So that's the problem we're going to look at. So if we were to take just a point, now we could take a point on the surface or we could take a point anywhere because the same thing's happening throughout the water, okay, all the way down to the bottom, okay. So just imagine we could pick a point in the surface then, okay. So we've got a point in the surface and we can look at the forces acting on that point. So one, you're going to have the force of gravity acting down the way, so we'll have a force Fg. So the force of gravity, force from Newton's second law of mass times acceleration, so it's mass times acceleration, it's just acceleration of gravity which is acting down the way, okay. So we'd also have a force acting in this direction, which is a centrifugal force, okay. So that force there would be our, call it Fc, and that would be mass times the acceleration, so that would be like a circular acceleration, okay. So then if we were going to look at both of these, and we're looking at it in terms of a potential energy, so we can work out the potential energy from these two forces. So we know the potential energy V is equal to well, I won't get through the full equation, I'll just keep it simple because you're probably used to seeing it anyway. So we said that the potential energy here is just the same as the potential energy you get whenever you look at a ball and the Earth's gravity, okay. So it'd be a mass times gravity times a height, so the height there is just the height Z, okay. So we'll call that V. V is the potential energy, mgz plus, well, it's going to be this potential generated from this force here. Now that force there, we can rewrite that over here. We can say that m times this AC, well, we can write that value of the acceleration is going to be equal to v squared upon r, okay. So that's the centrifugal acceleration, which is opposite to the centripetal acceleration, which tends to act in the towards the centre. Now I've got a video on centripetal acceleration and also angular acceleration, angular velocity in the snippet section. So if you're unsure about those things, get in the snippet section. There's a whole half-hour video there based on those things, okay. So that means that we can then write this thing here as steady ma. We could write that as mv squared upon r, okay. But we also know that v equals r omega. Again, that's in the snippet section, so you can check all that out if you're unsure about any of this, okay. So that's going to be equal to m times our, well, that's going to be squared, so it's going to be r squared omega squared upon r. So finally what you're going to have is m times one of the r's cancels by m r omega squared. Okay, so we've just rewritten this. Okay, so that's now going to be this force here is going to be m r omega squared. Okay, now the potential energy here due to this mr omega squared, well, as you move in towards the centre, your potential energy is increasing. Now you kind of know that if you were to if you were stuck in a roundabout, if you sat right in the centre and then if you let go, you would just go flying off in that direction there. Okay, and if you were further you go out here, your potential energy decreases. Okay, so potential energy is increasing as you move in towards the centre, but we've defined this direction here as a positive direction, so we're actually moving in that direction there. Okay, so it's going to give us that negative sign. Okay, so you're actually going to have then our value, if I just redo that, it's going to be I'll just put the minus sign in for that there, it just determines that direction. Okay, so now it's the potential energy, so to get the overall potential energy, we'll integrate the force with respect to the value of distance. So it's going to be the integral from, say, 0 to r of our m r omega squared by dr. Okay, so it means that the overall potential energy can be written as m times g times z minus, well, when you differentiate that with respect to r, so that becomes 2 and then it's a half, so it's going to be minus a half m r squared, okay, because that's 2, so it's a half and a 2 omega squared. So that there is our potential energy for a little point sitting in that bucket when it's rotating. Now, when you've been rotating round, eventually it rotates round and it finds an equilibrium position. Okay, so it ends up with a surface that sits like that. Okay, and if you're keeping the angular velocity at constant, eventually this will find an equilibrium point. Okay, so the surface, it will be a curved surface, but it won't be moving. Okay, it won't be changing shape. It'll have a fixed shape. Okay, so it means that if it then is a fixed shape, it means that all of the forces in that then at that point must be balanced. Okay, so if all the forces are balanced, then it means that from this simple equation here, that means that this potential here, overall potential is a constant value. Okay, so if we pick the point for a constant value to be actually just the surface of this, to be this surface, then we're able to then to say that this mgz is just equal to a half mr squared omega squared. Okay, now what we're looking for here is z as a function of r. Okay, so it just means that what we can then do is we take our mg down, so you're just going to have z as a function of r is just going to equal, well, it's going to be 1 upon 2 mg times m r squared omega squared. Okay, so the m's going to cancel out, so you're just going to have z as a function of r, that's just going to equal 1 upon 2, m cancels out, and you're going to have r squared omega squared upon g, so it's 1 upon 2g. Okay, so that there, I'll just rewrite it again down here so it's a bit here. So z of r is going to be 1 upon 2 r squared omega squared upon g. Okay, so that there is the shape of that little, the shape of the new curve. Okay, Now that there is the equation of a parabola. So if we were to look at that shape there, it would just be like a parabolic dish. So there would be a focal point here. So if, imagine it was actually a parabolic dish and these are coming in straight, then we would have a focal point here. Okay, so that will come up to a focal point. Okay, just like that. Okay, so that there is the equation of a parabola. Okay, so the shape given here is given by this here. Of course, it's in polar coordinates since it's a function of r here. Okay, so thank you for listening, and goodbye.